hopefully this time my computer won't decide to stop recording and stop being connected and just go to sleep. I don't know why that happened, but it did. So yeah, for anyone watching this recording, sorry. Only the first 5 minutes of automatic reference counting is going to be uploaded because the rest is gone forever. So, but now we're going to talk about the most important part of the class today, which is protocols. And in fact, this might be the most important kind of sub-lecture that we go over for Swift. There's a lot of code in these slides. I have the nice code animations for some of them and not for others because of time. So, bear with me as I go through it. Hopefully it'll animate okay. So, protocols. And as per usual, I'm not in focus. Protocols. Did we not click? Okay. This is off. My clicker's off. That was the problem. There we go. Okay. Protocols. So what are protocols? In Swift, protocols to start with are very similar to interfaces. If you're familiar with interfaces or abstract classes in other languages like C++ or C# or Java, I think Python has interfaces as well. I'm not terribly familiar with them. TypeScript, I think, also does. So they're in a lot of languages. So protocols are a lot like them, but not exactly like them, which is why we have to talk about them in detail. This is another kind of type. So we have our function types and our reference types and our value types and all that stuff. And now we also now have protocol types. We're gathering a collection of types like Pokemon. Got to catch them all. Protocols, though, if we want to talk about what they actually are, rather than kind of stuff around them. They are a blueprint of requirements for other types. So types, if you'll recall, are kind of a blueprint of how to store something in memory. And protocols are a blueprint of how to write a type, okay? So blueprint of a blueprint, if you will. In a protocol, it's going to look a lot like a class or a struct. The main difference is that you do not ever provide implementation details. If you put in a function, you don't put the function body. If you put in a stored property, you don't ever actually store a value. You can't ever actually create an instance of a protocol. You can't instantiate it. You can't call an initializer of your protocol type and allocate that memory. It is a guideline for how you write other types. Cool. Okay, so why would we ever do that? Well, we'll take a look. So what do we do with them? So whenever you want to use a protocol, you have a type of yours, such as a struct or an enum or a class. Those are the three types that can adopt protocols. They adopt a protocol. And types can adopt any number of protocols. In a way, this looks a lot like inheritance, right? Where you have a subclass and a superclass, right? But your superclass is a protocol. It's kind of weird. It's not the same thing, right? Whereas a subclass and a superclass, they are defined in very similar ways, right? But because of this weirdness that protocols have, you are allowed to inherit from or adopt many different protocols. So you can have many protocols that you are conforming to. So, and that's the next thing. You adopt the protocol in your type declaration. You say, hey, I'm going to use this protocol. I'm going to be like this protocol. I'm going to inherit from this protocol. Those are all valid ways of saying it. And then later on in your body, your type body, you have to actually do the things that the protocol calls for. And that's called conforming to the protocol. Okay, so you adopt it, you declare that you adopt it, and then you conform, okay? Anytime we have a type that conforms to a protocol, we can then use that type as the protocol. So I mentioned you can't ever call init on the protocol type, right? You can't say, oh, my protocol, open parentheses, close parentheses, haha, I've created a protocol instance. That's not a thing. But if you have, say, a variable that is set to be the type of that protocol, you can instantiate any other type, like a class or a struct, that adopts that protocol and store it in that property, or a reference or value, variable or constant, whatever you want to call it. So, and as I said, if this sounds similar to inheritance, it is. It's basically the same thing, except your superclass is a little weird and different. I don't know, maybe I'm running out of memory or something, but if these keep crashing, I'm going to have to like compose them together in like iMovie or something. It's going to be really annoying. So hopefully it doesn't happen again. We are now recording once more. Yeah, that was weird. Okay, so yeah, so if this sounds similar to inheritance, it is. And in other languages, when you use something called interfaces, which is what protocols kind of are, but not exactly, then this is also called multiple inheritance. We don't really call it multiple inheritance in Swift because we use the word adopt and conform, and Apple likes to be weird and different, but it's basically multiple inheritance. Okay. So let's take a look at how we actually do this in code. So this is a protocol. This is the syntax of a protocol. Let's say we're creating a protocol called content, okay? And let's say that's, for example, let's say that we're creating a content management system, something that allows you to, manage a bunch of different kinds of content like videos or blog posts or tweets or videos or something like that, right? So to start with, we'll create this protocol called content. This is going to be kind of the blueprint for any other kind of content we would create, right? So here we're going to say, okay, so any piece of content needs to have the property title, okay? And it needs to have the type string, and you need to be able to get that property and set that property, okay? So what we're saying there basically is that this property needs to exist, it needs to be retrievable, and it needs to be modifiable. You need to be able to mutate it, okay? And then we do the same thing with this content string as well. So anything that adopts content can conform to it by implementing a title and a content property that you can read and modify. And the way we do that looks like this. So let's say we're going to create we'll have our struct, it's called blog post, and it's going to adopt content. So we're saying, okay, it looks a lot like inheritance because it kind of is, right? And so we're going to say, blog post : content. That's saying, hey, we're adopting content, okay? Now, in order to conform to content and not get a compiler error, we need to have a title property and a content property that match the requirements that content has called out. So, to start with, we can just create a property called title that has type string. It needs to have the same name, the same identifier, it needs to have the same type, okay? A stored property like this by default can be gotten, so you can access and read it, so get is satisfied, and then it can also be modified and mutated, so set is satisfied. Okay, so when you see get set like that, that means typically, yeah, you can use a stored property. You can also use computed properties, but you need to provide a get and a set, sub method on those computed properties. Okay, cool. So, and then we also have to do this with content as well. That's another stored property. So now that we've done this, we also might have our own other things that we want to do. A blog post has an author, maybe it has comments, maybe it has a bunch of other things that are unique to a blog post and don't belong with other things that are also content, okay? So anytime you're, creating a type that, adopts and conforms to a protocol, you're probably going to, have a bunch of other things inside that type, other properties and functions and whatever, that are not defined in the protocol, and that's okay, that's expected. So, protocols can also inherit from each other. So here, we are having the content protocol inherit from the identifiable protocol. Now, protocols, like other types, can inherit from multiple protocols. And what this basically does is it combines all the requirements into that one protocol that you have defined. So in this case, the content protocol now also has, if you're saying I adopt the content protocol, you're also saying I also adopt the identifiable protocol, which means you have to conform to it. So if you write identifiable and then you don't make a change to blog post, you'll get a compiler error saying, hey, blog post doesn't conform to the identifiable protocol, okay? Because that's been combined and it's a part of the kind of contract between content and blog post, that blog post implement whatever identifiable requires. Now we haven't defined identifiable here on the slide because it is a protocol that exists in Swift. It's one that Apple provides, and it only has one requirement, which is that you have a property called ID, and the type of that property is something that can be compared to other types of the same. So it could be a string, it could be a double, it could be an int. There are many things that it could be. I think it needs to be a value type, right? But basically, it doesn't have to be a specific type. It just has to kind of fall into a category of types, right? And we'll talk about that later on as well, how you can put the same sorts of requirements into your protocols if you so desire. But for now, all you need to know is that if you implement the identifiable type, you need to have a property called ID. So we have a property called ID here, and the only requirement on that property is get. It is not a get set property, it's just a get property. So we can set this to let. We can have it be a constant. It doesn't need to be a variable property. It can be immutable. So it only gets set once, and then after that you can't change it. Okay, so that's inheritance with protocols. Now we can take a look at conforming to multiple protocols. So you can conform to multiple protocols via inheritance, like we did before with content and identifiable, right? However, I did mention you can, using a comma here after content, blog post : content, comma, you can still have more protocols that you conform to. This is helpful for if, say, you want your type to conform to multiple protocols, but you don't think that, we don't feel like content has to be taggable necessarily, right? Anything that adopts content doesn't necessarily have to adopt taggable, right? We don't think that's required. We just think that some should be taggable, but not all, right? So in this case, we just have this protocol taggable, and then var tag set string get set, and then we basically are saying, cool, we have a property called tags, it's a set of strings, and it's mutable, right? So once again, down here, we say var tags set string, it's a stored property, we're conforming to the protocol taggable, which we adopted, in addition to the protocol content, which we have also adopted. You can also conform to protocols and adopt them via extension. So you can write an extension on blog post down here on the bottom that adopts the protocol queryable. We've defined that up above. Queryable requires that you have to have any type that is adopting queryable conforms to it by defining a function called matches that takes in a property named query that has a type of string and returns a Boolean, okay? You need to match all of those things if you want to conform, and if you attempt to adopt the protocol and you don't conform to the protocol correctly, the compiler will tell you, and it'll give you a little handy, helping hand. Sometimes it's bad at it though, so don't rely on it entirely. So here now, what we've done is we've said, hey, we have an extension on blog post, okay? It adopts queryable, and then within that extension, we can create a function. All right, so you can adopt protocols in extensions, and this has implications that we're going to go into shortly for things that you can do with Apple's default, types that they provide you, right? Of note, if you do conformance within your extension, then you end up with a situation where, because extensions cannot define new stored properties, you would have to use computed properties if you wanted to do all of your conformance within the extension. But luckily, you don't have to. If, let's say, Queryable also had a property requirement, Swift is smart enough to know that if there exists in your code, in your module, an extension of your type that claims to adopt the protocol, you do not have to do all your conformance inside that extension. You can do it in other extensions, or you could do it in Okay, I think we're back once again. We've plugged in, so hopefully this won't keep pausing us. Right. Okay, so you can basically kind of mix and match your conformance across multiple different kind of code blocks as long as it's still within the scope. When you do an extension like this, it is, anything within that extension block is within the scope of the type that it's extending. It just has some rules like access control rules, like the private thing that we talked about earlier. Cool. So, as I mentioned, this means that you can define custom protocols and then have existing types that Apple owns or that you get through libraries or anything like that you include. You can have those types conform to your protocol, which means that you can have those types act like your protocol type and use them as if they were your protocol type wherever you need them. So our queryable protocol, for example, we can make it so that strings are queryable. It's basically just calling the contains method on the string, right? But it's kind of cool. You can basically, not only can you extend strings functionality, but you can do it in a way where you say, oh, string? No. You're a queryable. You're mine now. You made this, I made this, right? Old meme. And so now you can call on any string type the matches function, and you can also treat any string type as a queryable type. And we're going to get into that whole treating one as the other shortly. So like I said, my animations are bad in this later half because, time. But okay, so here's a large piece of code. Okay, so what this is basically going over is the concept of default implementations. If you're familiar with abstract classes in other languages, this is very similar to, but not quite the same as those. Basically, whenever you have a protocol, you can provide a default implementation for any of its functions that it requires. Is that a squirrel? What was that? That was weird. You guys heard that, right? That was so strange. Mouse, yeah. Basically, here we have our protocol content identifiable. We have now added a new function requirement on the protocol that says, hey, anyone that implements, that adopts me or implements me, they need to create this function, right? Mutating func update with new content string. Okay, so here we can then say, well, you know what? Because the thing that this function does is going to be the same everywhere, right? We find if we have our blog post and we write, we write our update function on blog post, and it's just, oh, content equals new content, and then we go to our tweet, right? And we do the same thing, and we're like, gosh, these functions are all the same, right? They're all the same. I'm implementing the same each time. What you can do is provide a default implementation. So the way you do that is by extending the protocol type. So if you do extension on a protocol type, you can provide a concrete default implementation for any functions that you have as requirements in your protocol. If any of note, if any type that is adopting the protocol chooses to write its own version of the function, that will, for instances of that type, override your default implementation, okay? But they don't have to use the override keyword because you're a protocol and it's a whole thing. So it's not exactly the same as class inheritance. So here on the bottom, we have our first pieces of code that are actually using these things we've been defining. So here we'll create a blog post. It's pretty empty, pretty bare bones. It just has new post. Someone's testing your system, whatever. So then we can print post.content, right? Prints new post, dope. And then here we can do post.update with a string, right? It's not shown here because it's in a ... but the blog post does not currently have a update function within it. It's not required to conform to the protocol content because content is providing a default implementation, right? So you don't need it. You could have it if you wanted it, but you don't need it. So blog post currently doesn't, which means post.update is calling this default implementation that we've provided in the content extension, which means that now when we print post.content, we get updated post because it's been changed. Cool. Okay. Any questions about default implementations using extensions? I know these are a little bit dicier than the other pieces. No? We're all good? Okay. So next we can talk about protocol composition. Let's say that you as a user of, in your code that's using these types that you're defining and creating and building, right? This architecture you're building. You're now writing the main.swift that's using these things, right? Or you're doing it in some other part of code, but basically you're trying to use these things. If there's functionality that's defined within one protocol and that's also defined within another protocol, and you want to make sure that the type that's being passed into you is a type that conforms to both protocols, you could say, oh, okay, then I'll just find a list of all the types that conform to both protocols, manually by hand, and I'll write a function for each one, right? And I'll have them all wrap around and call to the same underlying thing and all that stuff. It's very complicated, very messy, and very, it doesn't work if you ever add a new type that conforms to both, right? Instead, what you can do is you can do what's called protocol composition, where you use a single ampersand and it creates a composite type where it's saying, hey, the type here must be something that conforms to both queryable and taggable. Okay? So in this case, tweet, the struct tweet, conforms to both queryable and taggable. It conforms to both because the protocol content conforms to taggable. We've changed our mind. Now we think that all content should be taggable, but we don't think it should all be queryable, right? So tweet implements or adopts queryable, and content adopts taggable, and tweet also adopts content, which means it gets both, content identifiable, taggable, and queryable, basically, right? Tweet is all of those things, okay? So here we're saying, hey, this input parameter on the query all tags function, we want it to take in the only kinds of valid types that you can pass into this are types that adopt. I keep using implement, apologies. That's the terminology with interfaces. It's how I was taught this concept, and I'm trying to be better. So if I say implement, I mean adopt or conform, or adopt and conform. So bear with me as I try and adjust my language for you all to be slightly more accurate. So the input parameter must adopt both queryable and taggable, and as a result, inside of this function, whenever we use the input parameter, we can call any functions or properties that were defined in the queryable and the taggable protocol. And that's the only thing that we can call. So if we tried to say input.tweeter inside of this function, it wouldn't work because what's being passed in is not guaranteed to have that property. The only things it's guaranteed to have are the things defined in queryable and taggable, which we've seen before earlier, but as a reminder, that is a function called query or matches query and a property called tags, right? These last two things defined within tweet are the two things required by taggable and then queryable respectively. So within that function, we can call input.tags, and then we do this all satisfy thing, and then we can call input.matches. And we can do that because those are both guaranteed to exist, because we know that whatever type was passed in adopts and conforms to both queryable and taggable. So then down here, we can define our tweet. We can say print query all tags from tweet, and we have it print true. This initializer is kind of, bereft. I realize it's, there's some things missing. It is what it is. I just wanted it to not go off the screen. So, not technically syntactically correct. It's missing a tweeter, I think. Anyway, okay, so any questions on protocol composition before we?
Function, query, or tags is within the scope of the struct? Or
Are you asking, is it?
within the scope of that tweet, struct, or the protocol?
Yeah, so that function is, so the question was, is the function query all tags within the scope of the tweet or a protocol? The answer is no. Query all tags is in global scope right now. It's not indented. It's not within the brackets, right? If you count your brackets, right? It's just in global scope.
So it can access the variables from the tweet.
It can access anything from tweet that it can't access anything from tweet. Not really. What it can access is anything defined or anything required by queryable and taggable. So if we go back to, where's queryable? So queryable, all queryable requires is this function. So that means we only have access to that function, okay, within the parameter that gets passed in. And then taggable is back here, and that has this tags property, okay? So we can access the tags property and the query function. I wish I could get this to like skip. Instead, it just queues up all my moves. So now we're gonna probably shoot way past where we were. Yeah. So because queryable here, the type, in the composition here, queryable is basically saying, hey, the input parameter is a type that adopts queryable. So whatever input is, it has this function, matches query, right? Guaranteed. And it also, because it's taggable, has the tags property, guaranteed. And that's the only things that are guaranteed on the input parameter. So we can't access anything else that was passed in. Like if tweet gets passed in, we can't access tweeter or anything else, right? Not even the stuff defined in content, okay? So like ID and title and whatnot. If we wanted to have access to things defined by content, we would then have another ampersand after taggable and content, right? Does that answer the question?
And also, why are we setting the ID?
It's just so I didn't have to write the full so I didn't have to pass in the parameter in the default initializer on the struct because I wanted the code to be small, but I wanted it to be technically correct, but then I forgot to do it for the tweeter variable anyway. So apologies. Yeah, it's nonsense. Don't worry too much about that part. The important parts, I probably could have like dotted this stuff because it's not important. But yeah, the two things we care about right now are tags and matches, and the fact that because tweet adopts and conforms to both queryable and taggable, we can pass it into the query all tags function correctly. Cool. Any other questions? Okay. So, boxed protocol types, also known as existential types. In some future version of Swift, anytime you want to refer to a protocol as a type that you are defining for a property or variable or constant, you will need to use the lowercase any keyword every single time. That is not currently required by the compiler, but it is considered best practice. The any keyword indicates that this is a boxed protocol type. Essentially, what it's saying is anything that implements content is allowed here. Anything that adopts and conforms to content, any type, can be used here. So here we're defining a dictionary. The dictionary has a key of string, that's its type, so you access the values of that dictionary using a string key. And then the value type is set to any content, and content is a protocol type, right? So what we're saying is basically the values of this dictionary can only be types that adopt and conform to content. And that's what that is. You will be able to you'll be able to write this without the any keyword, okay? But it's doing the same thing. Basically, it's creating a special box around the type. It's a little bit expensive, right? But it's saying, hey, we're gonna kind of box out a type here called, any content, right? And within this, dictionary, things that get stored within there, right? It's not super efficient because, we know that some things that implement content are, really, really big, and some things that adopt and conform to content can be really, really small. But we give a big size so that we could fit anything in there, in that spot, right? So it's like one of those weird, tiny implementation detail things. But the main point is that you are always doing this whenever you're setting a property or a return or a parameter to a protocol type with the expectation that any type that implements or adopts and conforms to the protocol can be used there. You are creating a boxed protocol type, which is also called existential types by some people who like to be fancy. I think boxed is a funner way of saying it, so I say boxed. But yeah, so this is something to keep note of. Basically, what we're saying here, any makes it very clear. We're saying that the things that are allowed within here are anything that implements content. We could have a blog post for one value and a tweet for another and a video for another. And they're all different types, but they all implement content. And then what that also means is that if we ever access those values from this dictionary, we will only be able to use the properties and functions defined by content, unless we cast it to its underlying type. But that's something we'll go over another time. So, in addition to boxed protocol types, there is something called opaque protocol types. Opaque protocol types are a kind of defensive measure that you can use for protecting your API from misuse. They're similar to access control in that way. They don't have a huge logical impact on your code, but they do change how other people or yourself uses the code that you write, okay? So essentially what you're saying whenever you say some protocol type, here in this case, we have this getPost function that takes in a key parameter, right? Or a parameter called key that has a type string. And we are saying we're going to return some content, right? So what this means is if we ever call this getPost function, the type that comes back is always going to be content. However, internally, we always know that the type that we're returning is something very specific that conforms to content. So the distinction between returning any content and some content is very, very small and thin. And not super well illustrated here, but also it's hard to find good examples for this too, just because it's kind of an edge case thing. But basically, if sort of, at compile time rather than runtime, if you know at compile time that you are using a specific concrete type that adopts and conforms to your protocol, but you only want to pass that protocol, right? You only want that protocol type to be what is accessible to anyone, calling your function or passing into you, then you use the some keyword in front of your protocol. Yeah. So what this means here is that, let's say, we have this get post, right? What this is going to do is it's going to go in here and it's going to look for content using that key that gets passed in, right? And it's going to try to conditionally cast it to blog post. Okay, we're gonna say, hey, we got this thing from the dictionary. We don't know what it is. We know it's content, but we don't know what kind of content it is. Let's use as question mark to say, okay, well, if it's a blog post, then we want to just say, okay, cool, here it is. It's a blog post, right? If it's not a blog post, then we'll just say it's nil, right? Of note, this function is somewhat nonsensical, okay? Because then the next thing we do immediately is return it as some content, right? Which means that we say, oh, cool, we got it. All right, cool. So now that we have this concrete blog post, we're only ever going to return it to the caller as content. So we're going to basically, cast it from content to blog post and then back from blog post to content. Terrible example, but it's what I had. So, of note, the proper way to write this function would basically be to drop this as question mark blog post and then have this return any content with a question mark, because you're just returning whatever's in the dictionary content. And then you return it. It comes to the caller as content. Cool. Okay. That's opaque protocol types. Any questions about this kind of weird thing that you can use but don't always or frequently use with protocols? Cool. Okay. Delicate pattern. So let's go look at Xcode a little bit. Also, it appears that plugging the computer in did, in fact, keep it from breaking. So, okay. So in Xcode, let me get this pulled up. Boop, boop, boop. Boop. Create a new playground. Have to give it a name and everything. Okay, here we go. Let's make this bigger. Okay, so we've got our playground here. Okay. So very frequently, as we talked about before, you'll have, let's go back to kind of our example from the automatic reference counting. So we're going to end up having a class called tree, okay, and a class called leaf, right? And we want our tree to have a leaves, and here we're going to actually do it the way that you probably would, right? We're going to have a bunch of leaves, okay? So tree has many leaves, right? But a leaf only has one tree. Okay, so we're going to have tree equals nil. And then here, this can just be an empty, and that's fine. Okay, so this is what we've got, right? Now, let's say that we have a function called dropLeaf, right? And this is going to, basically remove a leaf, right? From our leaves, right? So remove at, we'll call it, yeah. So first we'll get the index of it. Let index equals leaves dot leaf dot index. No, dot first. Sorry, dot first index where. Leaf. Okay, so where the first thing is the leaf, and this needs to be wrapped in these guys. And it is, sorry, it's like all the way over here. I can't quite see it. Right, leaf needs to be equatable. Right. We can make it a struct. That'll do it. I think, right? No, okay. Well then, all right, so what we're going to do is we'll have leaf implement identifiable, and then we'll have our ID, and we'll make an int, and we will set that to 0 for now, this is not how it'll be. We're going to create an identifier, but we just want to get this done. So now we'll say .id equals .id. Cool. Okay. And then, actually, rather than getting an index, because we have an ID, let's go ahead and just make this a dictionary instead. And we'll use the ID as the way that we access things in the dictionary. So here, now we can just say leaves at leaf.id equals nil. And this will remove the key and the value from the dictionary. Okay, so we have our dictionary, it's leaves, right? And we have this ability to drop a leaf, okay? Cool. So now let's go ahead and say that we have something like age, okay? This is, like just our kind of age of our leaf, right? Now let's go ahead and remove these so that we have to create an initializer, and Xcode lets us do this fun thing where it, nope, not what I wanted, where it will, oh, okay, it's not going to make an init for us. That's sad. All right, that's fine. If we just start to, it'll help. There it is. Cool. So autocomplete, but we don't need to take in a tree. I guess we could. It's fine. So let's say that we have age, right? Now let's go ahead and make age private, right? And yeah, because let's say we only want age. We only want a leaf to modify its own age, okay? So now we'll have a function called, say, age up, right? Or pass time maybe is better, okay? So now we're going to have time pass, we're going to have the leaf age, and if the leaf gets old enough, we want to drop it, okay? We want the tree to drop it. We don't want it to be in the tree anymore. Fall has come, it's time for the leaf to die, okay? So we're going to, pass in some amount of time that has passed, right? We'll just call this like pass time, pass time, time int. I've decided I'm not gonna try and be clever with the argument labels and the parameter names, just because I don't have time for that. So we're passing in time, and then we're going to say age plus equals time, okay? And then we'll say if age is greater than 1,000, seconds, minutes, whatever, right? The unit isn't terribly important for our example here. So now we want to be able to call tree.dropLeaf, right? Like so. And we'll pass in self, and yeah, so now it's going to drop a leaf. And in fact, we can actually modify this if we wanted to in order to, do the thing, right? Now, let's say we also want to have a bush. Okay, here's a bush. Bush has leaves. Cool. Okay, it's all very similar. Yeah, cool. We got a leaf. We got a bush. Oh yeah, this is great. Right? Now we're gonna have drop leaf. Now we have leaves. Okay, and a bush. Okay. Now this means that if we ever, create a leaf, it's expecting a tree, kind of, probably, right? And so now it's like, oh, I don't know. Do we? I realize I need to make that weak to prevent a reference cycle. See how easy it is? Even me. I do it all the time. So basically now we have this situation where we have a bush and we have a tree, right? They both kind of do the same thing, right? They're both going to have this drop leaf function that does basically the same thing, right? They'll probably have other things about them that are different, right? Like a bush might have like berries, and it's like a berry type or something like that, right? And trees might have fruits, and so on and so forth. They're exactly the same here because I'm writing a quick example, but they can have a bunch of other properties that we might care about, okay? So because we're seeing this similarity here, one of the things that our minds might go to immediately are protocols, okay? So here we can look at this, and let's just call this like protocol leafy, okay? So if something adopts leafy, then it has leaves, right? That's kind of, the naming convention, right? So it's a leafy shrub or a leafy bush, or not bush, but like a leafy plant, right? We could call it leafy plant if we wanted, but, so here's leafy. Okay, whoop. All right, so now if we look at this, we want to say, okay, cool. So the thing that's common between these two, right, is leafy is a int with a leaf, right? And we want that to be gettable and settable, right? We want to be able to change it if needed. And we have a function called drop leaf, which takes in a leaf, and that's it. Okay, cool. We can also, because the implementation appears to be exactly the same, right? We can say extension on leafy and provide a default implementation for drop leaf that looks like this. Okay, and so now we've done that. So now we can basically make this leafy, get rid of the functions because we don't need them. It's yelling at us. What is it missing? Oh, I'm sorry. Whoops. I misspelled. I made this leafy. It's leaves. There we go. And we need to make this a mutating function. Just in case our anyone who adopts or conforms to us is a struct, they need to be able to make it mutating. By default, functions are mutating as classes. They don't care if you add the mutating keyword, you can, but you don't need to. So, okay, cool. So we have this now. We have our protocol leafy, extension leafy that creates our drop leaf function. We have a tree that's leafy and a bush that's leafy. Okay, cool, great. So we've done all that. So now what we can do down here is say, okay, rather than this being a tree, let's just call this our like parent, right? The owner of us, right? You know, or let's call it our plant, actually, right? So our leafy plant, okay? So you can't, because the weak protocols, or sorry, not weak the weak keyword can only apply to things that are reference types. You can't use it on value types. And right now our protocol could be used on structs. It could be used on value types. So the compiler is yelling at us and basically telling us, hey, weak cannot be applied to non-class bound any leafy. Consider adding a protocol conformance that has a class bound, right? And what that's basically saying is, you know, you have to require, right, that implementers of the leafy protocol be classes. You can tell it, you know, oh, this isn't allowed to be a struct, which I think you do with. Let me double check that. I don't remember the exact syntax. So what is it? Non-class bound. So if we go, trying to escape that screen. All right, non-class bound protocol. Yep. Class. I was right. Okay, cool. It just wasn't quite showing up. So class like that. Unless they've changed it. Oh no, they did. They changed it. That was a Swift 4 thing. Yeah, it is deprecated. Is that what this is saying? Yes, it wants any object. Got it. Okay. So any object is basically a way of saying, hey, this is a thing, and now we don't have to worry about mutating because we can't be implemented by a struct or an enum, okay? And we're all good. Everything's nice, okay? So now we have this value of type leaf has no member tree. That's because we got rid of it, right? So we're going to rename everything here. This is going to be plant. This is going to be, again, leafy, or as we talked about boxed, you can also say any leafy, right? Although optionals, unfortunately, have to go on the outside of parentheses around it, which is kind of annoying, but it is what it is. That will probably change in Swift 7, but for now, it's how it is. So now we can say .plant equals plant. Okay, cool. So now we have our plant. So now we can call plant.dropLeaf, okay? And now whenever we have time pass for a leaf, then eventually we can have the plant drop it. So let's take a look at what this might look like. So we're going to create a bush called bush, and we're going to create our leaf1 equals leaf. And it's going to be, ID 0, age 0, and we will pass in bush. Okay? And it will accept, in plant, it will accept a bush because it says any leafy, and bush adopts leafy. Cool. So now here we will do leaf1 dot age dot pastime, sorry, and we will have 1001 units of time pass, right? And then we can, do bush dot leaves dot values. Dot keys. So we could print this to get an array of all the keys, right? We could do it here and here to see how it's different between the two. Boop, 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 boop. There we go. There we go. So it's saying that, right? And that's because basically we did not set it up to add the leaf to the leaves parameter here. So here we need to say plant dot leaves at ID equals leaf, or equals self, sorry. And we have to unwrap it, so we can just do optional chaining like so. Just in case it comes in nil, then we just don't do anything, right? Which does mean if you set this from outside, after the initializer, you'll want to do something, which you can do by making it a computed property with a setter, right? But we're not going to bother with that for now. So now that we run this, so now we can see that the array of keys on bush has 0 at the start, and then at the end it is empty. Now, what we have done here is what's called the delegate pattern. Basically, if you have a kind of parent type, like tree and bush, that implements a protocol, and then you have a sort of, owned type, like leaf, that is, owned by a strong reference by the parent types, by the protocol defining the parent types, and the kind of owned type has a reference to its parent through the protocol. That is, and then you call a function on it to perform some operation, potentially on even yourself. That's called the delegate pattern, delegation pattern, delegate pattern. Yeah, so basically, owning parent type, child type with a reference to the parent that owns it, and then the child can call things on the parent using protocols to hide the details of what the parent is, right? It only cares that the parent at least adopts this protocol, and that is the delegate pattern. So the slide called for me to explain delegate patterns, so I just did. Okay, so that is protocols. Does anyone have questions about protocols while I've got Xcode pulled up and can slam out some examples? Cool. Okay. All right, so we're gonna do it's at 10. We're gonna do 5 minutes here. So I'm just gonna, at the 5-minute mark, I will have us stop because we're close to time, and then we will go over further things about generics next.